Hi friends, in today's video I'm gonna talk about SN1 reaction or nucleophilic substitution 1 reaction. So the reason why it's called nucleophilic substitution is that we have a nucleophile in the mechanism, and the reason it's 1 because we have one reactant in the slow step, which is the rate determining step. Let's start talking about the conditions. So for an SN1 reaction to happen, we have to have a very good leaving groups. Here we have a list of good leaving groups. We have chlorine, which is the best one, and then we have bromine, iodine, OH2+. These are the best leaving groups, but chlorine is the best, and then going down, the strength decreases by going down. These are the bases of the leaving group. The weaker is the base, the stronger is the leaving group. And here are the poor leaving groups. So the weaker is the base, the stronger is the conjugate acid, and the better it is at the leaving group. So if we have a poor leaving group, then no reaction will happen. This is the first condition. For the second one, we have the substrate. The substrate is the carbon at which the leaving group or the good leaving group is linked and bonded. Here it has to be a tertiary substrate. We have 1, 2, 3 carbons next door, meaning that this one is tertiary. The reason for that is that we are dealing with carbocation in the SN1 mechanism, so we have to have the most stable carbocation. The third condition is the nucleophile. The nucleophile for SN1 reaction has to be a weak nucleophile in order to attack the carbocation after the leaving groups leaves. So here we have the list of the nucleophiles. Note, nucleophiles usually have negative charge, or they can be neutral but with lone pairs. Here is the list of the nucleophiles: iodide, bromide, chlorine, and so on. So here for iodide, it has negative charge, but usually it's not used as iodide. We add to it spectator ion, which is like NaI. Like here, we have an NaI, but here if we remove the Na+, which is spectator ion, will have an I-, meaning that it's a very good nucleophile. And the only weak nucleophile that we use usually in organic chemistry are H2O and alcohols like CH3, CH2OH, or CH3, CH2, CH2OH, and so on. So these are the weak nucleophiles, and these are the good nucleophiles, the strong. And in the last place we have the solvent. We don't worry usually about the solvent. It's the last condition. If we have all these conditions, then we won't look into the solvent. But it has to be polar and protic. The polar and protic solvents are usually water and alcohols. So let's talk about the mechanism. Here for SN1 reaction, we have two main steps: the slow step, which is the rate determining step, and the fast step. The first step is the one which determines the rate of the reaction. So here it's a first order reaction, since we have just one reactant participating in the slow step, which is the rate determining step. So for the conditions, we have chlorine, which is a good leaving group, and then we have a tertiary substrate, 1, 2, 3 carbons next door, meaning that we are good for an SN1 reaction. Then we have the nucleophile, which is weak. Recall, H2O is a very weak nucleophile. And the solvent, which is polar protic. Usually it's not mentioned here, but it's water anyway. So if it's water, we won't mention it 2 times. So we are good for an SN1 reaction. Let's start by working on the mechanism. Here we have the first step, which is the leaving group, which leaves. The chlorine atom will leave, and here it is. This is the first step, and this is the rate determining step. And then we have the formation of n carbocation. So since we have the chlorine atom that left, will be left with a carbon which is positively charged. Since it's missing one bond, we have the formation of a carbocation. So the second step for this reaction, this is the intermediate step. This is in the middle. So the leaving group left, and then we are left with a carbocation and a nucleophile. This is the intermediate step. The step number 2 is the nucleophilic attack. We have the carbocation which is positive. It will be attacked by the water molecule here. And here we have H2O bonded to the carbocation. And it's not a carbocation anymore since it has 4 bonds now. But the OH2 has a plus charge because it has 1 lone pair and 3 bonds to the oxygen, which makes it positive. So here we have the second step. Since we have a positive H2O, it has to be neutral. Then it will be attacked. It will be attacked by the H2O. Like it will grab 1 hydrogen from the H2O plus, and then we'll be left with an OH, a neutral OH bonded to the initial reactant like molecule, and a leaving group Cl minus and H3O plus, since the water, which is the solvent, and the nucleophile in this case gained 1 proton. Now let's talk about the reaction rate or the order of the reaction. An SN1 reaction is a first order reaction, meaning that we have just one reactant participating in the slow step, which is the rate determining step. This is why it's called SN1. It's a first order reaction. Now let's talk about stereochemistry. For this example here, we don't have to worry about stereochemistry since we don't have any chiral carbon. The carbon over here, it's bonded to 3 same groups, so it's not chiral. We don't have to draw all the options for the product. But if we have this kind of molecule with an H group, CH3 and CH2, CH3, we have to think about stereochemistry. Now I know that you're gonna say why here it's a secondary carbon and we are talking about an SN1 reaction. Yeah, as I told earlier, SN1 reaction requires a tertiary substrate or a tertiary carbon, but it can happen with the secondary carbon, but it's less common and slower than an SN1 reaction that happens with a tertiary carbon. So here we have 3 different groups: hydrogen, a methyl, and an ethyl, a chlorine atom. So once the chlorine atom leaves, the leaving group leaves, we're gonna be left with a carbocation, right? So this is a carbocation bonded to 3 different things, meaning that it's chiral. And since we have the shape here, which is trigonal planar, it's like a plan. It's like plan. See here, we have 2 options. The nucleophile, which is the H2O for SN1 reaction, can attack the carbocation from this side or from this side. It has the option of attacking it from this side or from this side, because it's not blocked by something here or here. We have 2 groups and 1 group on the bottom, so we have 2 possibilities. If it attacks it from this side, we're gonna call it a retention. It's a retention. And here, if it attacks it from the different side, like here, it attacks it from the same side as chlorine atom, so it's a retention. And if it attacks it from a different side, the opposite side of the leaving group, it's gonna be called inversion, because it's attacking it from the inverse of the back. So for SN1 reaction, we get 50% of the first product and 50% of the other product here. So here we can draw and OH here, CH3, CH2, CH3. This is the retention, and we can draw it from this side. It's going to push the hydrogen and the methyl group to this side. If it's attacking it from this side, it's going to push the whole to the other side. If it's attacking it from this side, it's going to push the whole to the other side as well. So we're going to get a racemic mixture, which is called a racemic mixture of 50% of the first option and 50% of the second option.